So now for the last session, we will move to masonry modeling, okay? So we will first start with micro modeling. So both today and Wednesday, we will talk about masonry, and we will mix micro modeling and homogeneous modeling, okay? So today I will explain how to do micro modeling for the in-plane behavior of masonry shear walls. And then I will show you how to simulate the same in-plane behavior, but using an equivalent homogeneous material that has a particular feature that can become orthotropic, okay? Based on the results that you obtain with a micro model, or based on the results that you can have from experimental results. Tomorrow, instead, we will do the same, but for the out-of-plane behavior. Now, for the out-of-plane behavior, it will be a little bit more tricky because you have to take care about the finite element formulation that you use, but we will see tomorrow. And the analysis of tomorrow will be slightly larger, so I will take advantage of that for explaining the parallelism, okay? So whatever we've done today was with a single processor, and tomorrow we'll also talk about parallelism. So I'm going to share my screen. Okay, and first I will show you what we are going to do now. So here you have another folder in day one, which is called Masonry Micro in Plane and Masonry Macro in Plane. So micro is micro modeling, macro is homogeneous model. Okay, so let's see first what I'm going to show you here. So the CAD model that we're going to do is this one. I think we have something in the chat. Oh, no, sorry, not tomorrow, Wednesday. That's right, Wednesday. So the last session will be Wednesday, not tomorrow. Forgive me. Okay. So today, micromodeling, Wednesday morning, out of plane, micromodeling and macromodeling. Okay, so let me open the Masonry micromodel in plane, which is the first model we are going to do now. We are going to do this example now in 2D, so not with a shell, but with a two-dimensional continuum element. So everything will be in the XY plane. This is the geometric model, and this is how we are going to assign material properties. So as you can see, everything is done with continuum elements. Let me switch off this one for a while. Everything will be done with continuum elements. So we're not going to use interfaces because in OpenSees there is no concept of interface. We are adding it. In fact, in the flyer, I've written that I would talk about also interface modeling. The problem is that in the last days, the OpenSees maintainers made some extra changes that actually prevented us from implementing our interface model. So I will talk about only continuum modeling, both in macro and in micro modeling. Then in a future webinar, I will show you how to do the same with interfaces. So as you can see, everything is modeled as a continuum, both brick and mortar joints, so with their physical length. And every component here will have the same damage TC 3D model, one with the properties of bricks and one with the properties of mortar joints. Then we're going to apply two steel beams at the bottom and at the top. And we will be doing a simple pushover analysis. And the results we are going to obtain for the micro model is something like this. Micro in plane. Okay. So here it has a quite fine mesh, but actually you can obtain very good results even with a coarser mesh. Let me show you a little bit what's going on here. So this is in terms of displacement, what we're going to obtain. So we first apply a vertical load, then we apply a constraint keeping the vertical displacement fixed of this wall. This wall is actually the Rainmaker wall tested at Eindhoven. I will send you also a reference for the material parameters and everything for this. And then we will be applying a simple pushover, and we will see how there is a formation of the different cracks up to the coalescence of a single diagonal crack, down to the failure of these two toes here. This is in terms of displacement. You can see the same in terms of damage. Okay, now it's nice for damage to change. Damage goes from 0 to 1. Okay, and this is the behavior in terms of damage. We see first the opening of tensile cracks here, then a progressive formation of diagonal cracks up to the failure of bricks where the different cracks coalesce in a single crack, and then finally the complete failure of the two toes in compression. Okay. Then we will simulate the same thing with an homogeneous model, starting with a simple isotropic model, and we will see that we are going to either underestimate or overestimate depending on which direction we choose, because you know very well that Masonry is orthotropic. So whenever we try to model it with an homogeneous model, most of the softwares has a nonlinear isotropic homogeneous model. So when you choose an homogeneous model, you have to choose one of the two directions for Masonry. You cannot choose both of them, of course, because your model is isotropic. So if you choose the weak direction, you will underestimate. If you choose the strong direction, you will overestimate. And then I will show you how to use a new material model that we put in OpenSees, which is called Orthotropic Mapper, which is basically a wrapper that takes any nonlinear isotropic model, and with few material parameters, it can change that model into an orthotropic one, and it works with any nonlinear model. So in this case, we apply it to our tension compression damage model, but it can be applied, for example, to the J2 plasticity to obtain the heel plasticity for orthotropic steel. Is the same. Okay, so let's clean this one, and we do the same here. Okay, so the first thing that we are going to do is to import once again 2D drawing of the main lines of this drawing here. So we go under geometry, and in the folder Masonry Micro EP, you have a basic drawing in VREP format, pretty much as we did with the reinforced concrete shear wall. So here you have all the lines. If you have a cut drawing, you can use this approach. Otherwise, you can directly draw face by face. Typically, when the bricks are regular, what I typically do is to draw a couple of bricks and mortar in such a way that it is a regular pattern, and then I copy paste it all around. And finally, I do a Boolean operation. Now, in this case, since I have already I have a drawing, I prefer to use this one, create all the faces, and then assign the materials. But it's up to you, whatever you prefer. So as we did before, we start with this basic drawing, and we need to convert everything into faces. So once again, we use the planar face command. We select everything, right click, and then we have all the faces here. The lines are still selected, so we can remove them by pressing cancel. Okay. So we remove the basic drawing, and now we have all the faces here. Perfect. Now I want to switch off the visualization of points for a while, because I need to select all the faces to assign material properties. So first we go into physical properties as we did before, and we start creating all the constitutive models. So the first thing is to create a constitutive model for mortar. So let's call this one mortar. We choose the same model we've used before, so ND plugin as the software damage TC3D. Okay, so the mortar joint here, if you take all the parameters can be taken also from the paper of Professor Lorenzo, the multi-surface plasticity interface model. Is the same shear wall tested there. So 850 and 0.15 Poisson ratio. Then we have 0.2 tensile strength megapascal. Then 0.008 fracture energy. Then in compression, we have 3 as the elastic limit, 6 as the peak strength. Then we have 1 as a residual strength. The peak strain is 0.02, and the fracture energy in compression is 7. Now here this value can be left as they are, but actually in this example I tested them and it looked like a little bit better to put 0.7, 0.7, 1.5, but actually it makes almost no difference, just in the post-peak regime. Okay, so instead for the miscellaneous compound, I use a Rankine surface. So I want to increase the strength of this material a little bit, so Rankine surface is fine for this purpose. I want to increase the biaxial behavior to 1.6, because actually one main problem that you have in this kind of micro models, when you use continuum models and you are working in 2D, you cannot capture the typical triaxial compression effect that you have in mortar due to the stiffness difference between bricks and mortar. It can be captured if you do a 3D model, because you can have a three-dimensional triaxial state of compression in mortar. But since in this case, this example is plane stress, of course you cannot have a triaxial compression. So you can do some trick, for example, incrementing the strength in biaxial compression, which is available, or increasing a little bit the uniaxial strength here. Then in this example, I was not using any damage because actually the first time I've done this example, the damage was not available in this model. But by the way, in this example is a simple pushover, it's not cyclic, so the amount of plasticity is not important in this example. Once again, we choose the Implex algorithm, so it will be faster, and automatic regularization. That's perfect. Oh, I want to tell you something about the automatic regularization. So as I explained before, OpenSees takes the input fracture energy that we gave here, and it divides this fracture energy by the characteristic length of an element. Now, probably if you are familiar with the crack band approach, the characteristic length of an element is its characteristic size. Now, depending on if you have read some papers about it, someone takes the diagonal of the element, someone takes the square root of the area, if an element is kind of regular. In OpenSees, they do something different. They take the minimum distance between the different nodes. Actually, this is very fine when you do micromodeling, because in this example, we are going to mesh it with a mesh size of 10, which is exactly the thickness of the mortar, okay? And the element is perfectly regular. It's a quadrilateral element with all the sides equal, so it doesn't make any difference. But let's say you want to model a very large model. You cannot use that fine mesh, so you can use something like one element for each brick, and the mortar will be a thin layer with its thickness of 10, and then the other dimension, which will be very large. And it is fine that OpenSees takes the minimum length, because in micromodeling, the crack will always be in the orthogonal direction of the thickness of the mortar joint. So the regularization will be perfect in that case. Okay, so just keep in mind that in OpenSees, the characteristic length is the minimum size of the element edges. Okay. Okay, so this one is our material model for mortar. Okay. Then we do the same for brick. Once again, it is a material, ND, plugin as the software, damage TC3D. This time, the brick has 17,700, 0.15 Poisson ratio, then a tensile strength of 2, 0.08 the fracture energy, then 20 as elastic limit, 30 as peak strength, 1 as residual strength, 0.002 as peak strain, and then 5 as compressive fracture energy. Then this value as the mortar, 0.7, 0.7, 1.0.7, 1.5. Rankine intention, 1.1 biaxial strength, 0.16 is the same, This value is not important here. Also in this case, I didn't have any damage at the time, so I want to replicate that example. 0. And the implex algorithm also here. Automatic regularization, make sure it is switched on, and we are fine. So we have mortar and bricks now. We just need one extra material model, which is steel. Steel will be elastic for these 2 layers of rigid beams. So we create a elastic steel material, ND, other ND, and elastic isotropic. Maybe we have 200,000. Hope it is fine. I don't see from here. Yes, 0.3. Okay, for the steel. Now, these ones are 3-dimensional materials. Now, as I told you, here we are doing a 2D analysis, and we want to do this analysis in plane stress because the wall is relatively thin. So we need to create wrappers, as we did in the shell example. In the shell example, we converted a 3-dimensional material to a plate fiber because in a thick shell formulation. Sorry?
Excuse me, in the brick property, physical property, you put C2 as 0. Is it by intention or?
No, probably I made a mistake. C2 as 0, no, it's 0.5, sorry. Thanks.
Yes, okay.
Okay. But in any case, I will send you the model because when I repeat this example, sometimes I do some mistakes. So thank you for the attention. Okay, this is fine. So as I told you, these are 3-dimensional models. Now we are going to convert them in plane stress models. In the shell, we have used the plate fiber because the shell has a thick shell formulation, so we need the out-of-plane shear, but we don't have the out-of-plane stress, the direct component, so the sigma ZZ. Now, in this case, we need to use the plane stress. So both the out-of-plane stress and the out-of-plane shear should be 0. So we need to convert all of those elements in plane stress. So we can write mortar 2D. We go under model, materials, ND, other ND materials. And instead of choosing plate fiber, this time we choose plane stress. Plane stress is very easy. We just need to select what is the 3-dimensional model that we want to convert. So this one is mortar 2D, and we choose mortar 3D. Then we do the same for brick 2D. Materials and the other ND materials, plane stress, brick. Then we do the same for the steel. Actually, it is not necessary because the elastic isotropic material can be automatically converted to plane stress. So it is not necessary to do a conversion, an explicit conversion. But in the file that I sent you, there was this explicit conversion, so I will do it also here. Elastic D, materials and the other ND, plane stress, and we choose the elastic steel. Perfect. Now we have all the 3-dimensional material converted to plane stress. We don't need any other material. So we can start assigning them. So we go under property. For the moment, I want to switch off the grid because I don't need it. And I'm going to assign these material models to the different phases of this one. So I switch off everything but phases. So I do not accidentally assign it to lines or points. So you may ask why, if you have drawn these lines for the mortar joint, why are you enlarging, and why are you extending these lines throughout the drawing? This is just because in this way you have all sectors of this drawing which is a quadrilateral surface, so it can be meshed with a structured mesh. Otherwise, you have to use a triangular mesh. Okay, so now everything here and here are faces of a steel material. So we drag and drop the elastic steel. So as you can see, when you work with solids, either in 2D or 3D, it's much easier. You just define the material and then you drag and drop. Instead, with beams and shell, you have to create the material, then you have to create the cross-section, and for beams, you also have to create the integration scheme. Now for solid, it's much more immediate, okay? Now we do something else. I first select everything, because here the most annoying thing of this part of micromodeling is to assign material properties. Now, first I select everything, and I assign the brick to D. And now I'm going to select only the pieces that I need for assigning the mortar. Now, since I don't want to act on these faces, I can hide them. So I do not accidentally select them while assigning mortar. So I selected the faces with steel, and then I can use the hide command that is here in home. I click hide, so I don't see them. Well, actually, I would like to hide also these lines. Hide. Later on, when we will show everything, we can click on show all and everything will pop up. Okay, so now back to only face selection. I need to assign mortar properties. So the mortar starts here and all the faces. That's why I told you, when you are doing a large model, probably it's easier not to do how I did it, because in this case I started with a 2D drawing and then I created all the faces. Sometimes it's easier if you draw a couple of bricks and mortar in a regular pattern, and then you copy paste them all around, okay? Because when you create a regular pattern and you assign the material and you copy them, the material will be copied as well. So that would be the nice approach. But in this case, unfortunately, I started in the wrong way. So, okay, so let me first select all of these layers for mortar. Okay, I drag and drop mortar here. Okay, and then I need to start from this one. Now, for example, I can show you how to copy paste them actually, because now that I assigned these, let me drag and drop the mortar. Actually, to speed up the things, instead of I'm going and select everything, which is quite annoying, let me delete these faces. I'm under faces, and I want to delete all of them. So let me show all actually. Show all, and I want to see everything. So now I will show you how you can use the copy paste command. So in this case, I was using the simple selection. Now in the other option, now that I have a regular pattern, which are these two layers, I can just copy paste them. So let me delete all of them up to here probably. No, something more. Okay, I delete them. Now I want to extract those faces. So I can show you something. Now I have two geometries, this one and this one, because I deleted what's inside. Now there is a command called extract. With extract, I can select anything, in this case faces, and I can extract them from the original geometry. Now what I want to extract is this regular pattern. So layer of bricks, mortar, bricks, mortar, in such a way that I can copy paste them, okay? Right click. If I go back in property, I can select the second one of the extract one, select, and I move it. I can click on the move command, or I can type the command here, pretty much like in AutoCAD. And now I want to move it from here to here. Okay, but actually after the, that's right. After the extract, I don't copy the material model, so I'm going to reassign them. In this case, I need bricks, bricks, Okay, only faces. These are bricks. Okay. And then I select these faces. But because the extract command actually does not copy the material property, but now that I assign it to this one, I can copy paste them. Just a little bit of patience. Perfect. Now I can copy paste the mortar. Perfect. Now I can go back to the full selection, and now I can finally copy this one all over the place. So I can type the copy command, and I can start copying it from here, here. I repeat the command. Couple of them. And I think the last layer, but without this, so I can remove back to only face selection and remove this last layer. So I can copy this one. So back to full selection and copy. Okay, perfect. So they are fine. Now the last thing that I did not assign was the mortar on these few layers here. So I go back to only face selection and I select this last layer that need to be assigned. And this one, oops, and drag and drop mortar 2D. Perfect. Now that everything is in place, as I said before, I can do a Boolean operation. So let's start by saving everything. Masonry micro in plane. Let's call it micro in plane. Okay, now that we have everything, all these geometries are separated. We need to do a Boolean operation, otherwise they will generate separated elements. So since they are all faces, when you have to do a Boolean operation, you can either go to the generic Boolean operation here, which is called merge, or you can use, in this specific case where everything is a face, you can use the SU faces, which is a simplified Boolean operation made for faces. Okay, so I can select them all. I do SU faces. Okay, and then what obtain is a single geometry, and the nice thing is that the property are retained. Okay, that's why I told you when your model is pretty large, it's better if you first draw a simple repeatable pattern, and then you take this pattern and you repeat it all around, and then finally you do a Boolean operation. It's easier because you can copy paste basically the material properties. Otherwise, it will take a lot of time to select all the mortar layers and bricks. Okay, so basically now we are done with our geometry. So pretty simple. Of course, this model was pretty small, but it is fine. So we have the geometry, we have the physical properties, now the element properties. Now in this case, it's pretty easy. Everything will have the same element. We are going to discretize it with quadrilateral mesh. So in element property, we add a new element, and we can call it quad. Now we go under material, quadrilateral elements. Here we have many of them, and here we choose just the standard quad element. This one here, you can choose if it is a plane strain or a plane stress, and we choose plane stress. And here you have to specify the thickness. Now in this example, the total thickness of the wall is 100 millimeters. Okay. And now we need to assign this one to everything. Now, before I didn't explain it, but by default, when you are on the property toolbar, you see the colors by physical properties in such a way that you can see where each physical property is assigned. If you want to do the same with element, you just switch to element, and now you see everything is transparent because you didn't assign any element. Now, in this case, we want to assign the same element to the entire geometry. So there is no need to go under subselection. We can just select the entire geometry and drag and drop the element. And now you will see the color of this element here. If you switch back to physical property, you see the colors of physical properties. Okay, we can save it. Now we have physical properties and kinematics in place. Now we need to create boundary conditions. So we go in condition tab, so we can see the assignment of boundary condition. Now the first one will be prefix at the base. So we go under model, constraints, and single point constraint and fix. Now in this case, we are fine with the default settings because we are doing a 2D analysis with only displacement degree of freedom. And we want to fix everything, so UX and UI. And we want to apply this constraint to the entire bottom line and press OK. Okay, so we have the fix down here. Now the next boundary condition will be the vertical load for the vertical analysis on top of the masonry. So we go in add, vertical load. We go under load, force, pretty much as we did for the self-weight of the shell. Now here we want to apply a uniform pressure on the top edge. Now the point is that we are doing in 2D, so we cannot apply a pressure. We need to apply an edge force, which is a pressure multiplied by the thickness of the wall. So we choose edge force. Once again, like the face force, is basically, in this case, is an edge force, so it is a force per unit length. And automatically STKO will do the nodal lumping for you. So when you go in edge force, you need to put a value. In this case, we are in 2D, so a value in negative y, which is 30, because we are simulating. If you see the reference paper for these walls, they have been simulated for different values of vertical pressure. There was 0.3 megapascals and something more, something like 1.2, and I don't remember the other. We are going to use a 0.3 megapascals times 100 millimeters of the thickness. That's why I put minus 30 force over length. And I select the entire edge up here. Okay, and now we have also the vertical load here. What else? Okay, here we need to apply an imposed displacement. Once again, as in the other examples, you can either apply a force and do a load displacement control, or you can apply a displacement. Now, in this case, it is a simple one story, basically, so it is sufficient to apply a force here, and it will be easier. Of course, if you have to do a pushover analysis of a multi-story building with different displacement ratio here, you cannot apply a displacement. In this case, you have to apply a force and then find the displacements using the displacement control. But in this case, an applied displacement is fine, and it's more immediate to apply. So we create a typical push condition. We go under load, impose displacement, prescribed nodal value. 2D, only displacement, constant, not relative, because it will not move in X in the first step. And we push it in X of 4 millimeters. Let me check. 4 millimeters. And we apply everything in this point, because we are going to push it in this direction. Okay, so we have also the push here. Then we need one extra boundary condition. Now in this example, we are going to first apply the vertical load. Then we are going to do the first analysis, and this wall will move downward. Then we want to fix the vertical displacement in such a way that the beam cannot rotate and cannot move in the y direction. Okay, So it is not sufficient to use an equal dot constraint, because an equal dot constraint will prevent the rotation, but the entire wall can uplift. In this case, we want to actually fix it at the vertical displacement it reached with the vertical displacement. So instead of using a fix, because fixing it at 0 means that after the vertical analysis, the wall will come back to a 0 position. We want to fix the top at the current position. So fix top. And instead of using a constraint, a single point constraint, we use a load, an imposed displacement load. We choose, once again, imposed displacement. This time, we say y equal to 0, but we don't know what will be the displacement at that point of the analysis. That's why we have this tool here. We can choose relative. Relative means I will apply this value relative to the current displacement at the moment this condition has been applied, okay? So since we will apply it after the vertical analysis, it will be 0 plus the current displacement, okay? So don't forget to put relative, otherwise if I don't put relative, it will come back to the original 0 position. So here you have all the description. And it will be applied to the entire edge. Perfect. Okay, now we can save it. Now we are done with boundary condition. We need to create the analysis steps, but first we need to define the definitions, so the load multipliers for this load. Now we need, for the vertical load and then for the pushover displacement here, we need a linear ramp because we are going to do a monotonic analysis. So we go in definition and we choose a linear model time series linear from 0 to 1 in a time of 1 second. Okay. But then we need another different time series for the prescribed displacement at the y direction, because this value here, even if we put 0, which is a constant, you may say, okay, but you don't need a load multiplier because it is 0, so you can multiply it by whatever number. No, it is not actually 0. Here it is 0, but in the Tcol code, it will become 0 plus the current displacement. So it is actually a value. And if we multiply with an increasing time series, that value, let's say it will be 0 plus 10, because it moved of 10 millimeters, it will be applied from 0 to 10. Instead, we want to keep it constant, okay? So we have 0 here, and it's fine. But when we apply this boundary condition, we need to apply it in a constant fashion. So it should not change during the analysis. That's why we can create another time series called constant. And OpenSees has a constant time series, which is this one, constant. So basically, the load multiplier will be 1 despite of the time step. Perfect. So these are the 2 time series we need. And now we can start creating the analysis steps. So the first one will be the recorder. Let's call this recorder, that's fine. MPCO recorder. Now we can write the results as micro in plane, because then we will be doing the macro in plane. We want to record displacement, reaction force, nothing else here. Then we want to plot material strain and material stress. Before, we have been using section fiber strain and section fiber stress because we were using beams and shells. So the section keyword is for Gauss points of beam and shells, and the fiber because we were using fiber section. Now, in this case, it is a solid. And before I told you that for solids, you should use the material keyword. Unfortunately, this is one of the convention of OpenSees, and we have to stick with it. So material point means for every Gauss point of a solid element. Solid means a 2D continuum or a 3D continuum. So material strain and material stress. And if you want to record the damage, same thing. We go under the custom material, we create another one. And now, similar to material point, we write material point damage. Okay. And we save it.
Excuse me, Professor.
Now, next step.
Like in OpenSees, when we assign a recorder for example, if we have a 2D frame and we want to record the displacement at the base or at the top, we usually we have the commands like we write the frame, the element, and then we whatever we want we can. But in this you didn't mention any particular name or the position of the, for example, if you want to know the stress or strain in the bottom, you didn't assign anything. You didn't.
Yeah, because by default, the MPCO recorder records results on anything, so on the entire geometry. If you want to record something only on one particular piece of your model,
Yes,
there is an option. I didn't mention it because I typically never use it. When I do a model, I typically want to see everything, and then I extract in the post-processor what I want from a particular position. But here you have the region command. For example,
okay.
if you want to record something only on, let's say on the bottom here, what
Yes.
you can do is this. You go under selection set, you create another selection set like this one, and then you select, for example, all the faces at the bottom, right click, and then I call this one set bottom. Okay, this is just a group, so it can be used by, for example, for select previous selection, or it can be used in the recorder to say, okay, I want to record this, not on the entire geometry, which is the default. Otherwise, I can put it here. So I want to record everything only on this geometry. Actually, I need to create a region for this. I need to create a region command first. Region. There is the miscellaneous command region. For a region, I have to select a selection set that I already defined. Selection set bottom. Now the region command is used in OpenSees both to create a region and to assign the relay damping. Now we don't need the relay damping here, we just need the region. Okay, now we need to move this one before the recorder, because otherwise the recorder will not be able to use one. So we can use this arrow here, we move it before, and then in the recorder, we select the region. We can have multiple regions, not just one, okay?
Okay.
So now in this case, everything you will see in the output will be just the output for this bottom series of elements, okay?
Yes, okay.
Now in this case, I don't want to do this. I want to record everything. But remember that if you want, you can.
Thank you so much.
Okay. Okay. I remove this one and I remove this one. No, sorry. Delete. Okay. Perfect. So the recorder. Now the next step is to apply the fixity at the base. So add fix. As you can see, the procedure is basically almost the same. Once you understand it, it's always the same. So constraint, and you add a constraint pattern. In this case, we only have single point constraint, which is the fix at the base. And this is the first condition that we apply. Then always before the first analysis, we need to apply the vertical load. So add vertical load. Once again, this is a pattern, add pattern, load pattern. Vertical load should be applied in a linear increasing fashion, so we choose the linear time series. The vertical load is a distributed force, so it goes under load. Why it goes under load? Because as I told you, it is a distributed force, but in OpenSees, this distributed force does not exist. STKO will actually write a series of load and nodal loads. That's why we have to put it in the load vector here. So we go here and we choose vertical load. Okay. And okay. Now we are ready to do the gravity analysis. So add vertical analysis. We go under model, analysis command, and it is static. Once again, for the same reason I said before, I choose a penalty method, 1 e to the power of 15, also here, because the typical stiffness of this one is similar to the one of the shear wall. So 100 millimeter stick, 4 order of magnitudes for the bricks, so it is the same more or less. We do, well, here we can use safely, since the model is relatively small, we can use a sequential solver, so reverse and UMF pack is fine. Newton is fine. The normal balance is not good with penalty, so we have to change it with norm displacement increment test. And 1 to the minus 4 millimeters is sufficient. We choose 100 iteration, even if it is not important, it's not necessary, because in this example, it will converge with 2 to 3 iterations. We use the print flag and we use the value of 1 because we want to see the convergence rate. Load control, just 10 steps. 10 steps of 0.1 lambda h1 is fine. And then don't forget to put the load constant and to reset the time step to 0. Okay, so this one is the vertical analysis. Oh, I didn't mention it, but in STKO you can customize your the layout of your application just by dragging and dropping these things here. Next step is to apply the 2 boundary condition for the shear wall behavior. So the second boundary condition, we said that is the fixed top beam. And so basically, after the vertical analysis at this point of the script, the wall will move downwards, so it will have a non-zero displacement in the x direction on the top. So it is here that we add another load pattern called fixed top. Okay, as I said, this fixed top should remain constant during the analysis. That's why we choose the constant time series. And the fixed top is a single point constraint, is an imposed displacement actually, because it is not actually 0. It is 0 relative to the current position. So it is a prescribed displacement. And we choose the fixed top. Okay. Then we apply the imposed displacement, which is our horizontal load. Same thing, it is a pattern, add pattern, load pattern, but this time we need a linear time series because this displacement should increase from 0 to the maximum value. Also, this one is a single point constraint, so we put it here and we choose the push. And this is fine. Okay. And finally, we need the last analysis. Save it. Once again, it is very similar to this one, so I clone it, edit, push over. Still, it is a static analysis. Penalty method is the same. The other things are fine. Newton, norm displacement increment test. This is all fine. Actually, in this example, I put a slightly better convergence, so 1 to the minus 6. But once again, it is not important. And here I've chosen to use 100 step. So 0.001, 100. And I don't need the load constant. Okay. So the analysis is done. We can save it. The last thing that we need is the mesh. Okay. Now, in the example that I've done before, I don't know if it is still loading. No, I used the mesh of 10 millimeters. So you will see actually that you will obtain a good result even with this one. So let me give you an example with a coarser mesh, like let's say 30. Okay, it will not be perfectly 10 millimeters like this, but it is still fine. Then in the example that I sent you can see the results made with the finer mesh, but this one will be basically the same. So done. Then we need to assign mesh controls on faces. We want to use a structured mesh with quad topology over the entire domain. So assign and accept, done. Now we can mesh it. Okay, so this is our mesh, not so many elements, just almost 5,000. We can save it, and we can run the analysis with the sequential solver this time. We are in micro 5p. Okay, so let it run vertical analysis. Now it is doing the horizontal analysis. It will take 1 minute more or less. Then as soon as this finish, we are going to do the homogeneous one. Now this one is a new element, is a new material in OpenSees, so we'll spend a few words. Okay, this one has finished. As you have seen, it took at most 2 to 3 iterations, and this is thanks to the implex algorithm. The implex algorithm basically, what is this one? Makes the solution stepwise linear. So it takes, actually it should take theoretically 2 iterations. The first one with the error, and the second one to zero the error. But in OpenSees, there is a different way in which they compute the residual, so it takes 1 extra iteration, but it is fine. So at least you are sure it converges. Be aware that you need to use a quite small time step. If you are not sure, you can do a series of analysis, decreasing the time step until you see no change in the response. But in the next version, we are trying to add an automatic time step based on the error computed by the implex algorithm. So this is our first implementation, but we are going to make it even more automatic. Okay, so let's go here and we can open now. This one is the one that you will open, so the one with the fine mesh. But we will see that this one is pretty much similar. Micro in plane. Let's remove the deformed shape and let's use the surface color map. As you can see, basically, the failure pattern is the same. Okay, I don't want to see the mesh edges. We can put the damage. Oh, I want to show you something about the damage, because if you remember, I told you that damage is a value that goes from 0 to 1. 0 means there is no damage, so everything is elastic. 1 means it is completely broken, so the strength is 0, basically. And a value in between is a portion of the material that's broken. So you know that damage goes from 0 to 1. If I plot damage here, you will see something strange. You will say, okay, but damage should go from 0 to 1. Why do I have 0.7 minus and 1.34 in points like this? You say, okay, there should be some error. Actually, it is not. Whenever you visualize a result, and this is true for every pre and post processor for finite element analysis, whenever you visualize a result which comes from the Gauss point, so the displacement is a result directly on the node, so it is fine to visualize it on the node. But when you visualize a result that comes from a Gauss point, which is inside the element, and you visualize it in a plot like the surface map, which basically assigns a color to the node, the value from the Gauss point is linearly extrapolated from the Gauss point to the node. So the value that you see here is not the real value. The real value is the one that is in the Gauss point. So why this value goes outside the bounds of the damage in this case? Now imagine this wall, this piece of element. It may happen that in this element, in one Gauss point, you have a damage of 1. In the other here, you have a damage of 0. If you deal, and they are internal to the element. If you do a linear extrapolation, you may actually see that. Okay, let me see a drawing, for example. Annotate. Okay, imagine that here you have a damage of 1, which is this value. Here you have a damage of 0, which is here 0. Then you have to linearly extrapolate this one from here to here. Then if you do a linear extrapolation, this is exactly what happens. Well, actually this should be 0. But here you have a value which is higher than 1, and here you have a value, oops. Here you have a value that is less than 0, okay? But it is just a common mistake that you do in post-processing, in every kind of post-processor. So be aware that if you want to see stresses, strains, damage, so all the variables in a Gauss point correctly, you have to use the Gauss point plot. That's why we used the Gauss point plot. Okay, so here you have two options basically. Clear all drawings. Okay. One option, if you want to see this one, and you know that, for example, for damage, I don't want to do an extrapolation, you can fix the maximum and minimum. I know that the minimum is 0, the maximum is 1. So whenever I have some value that goes outside, I simply clamp that value to the maximum possible, okay? So this is one option. Or the other option is actually to visualize the Gauss plot. Here in the Gauss plot, you have the exact value, no linear interpolation. So if I remove this one, and if I plot material damage, as you can see here, you just see those values. That problem happened in this element, in fact. As you can see here, you have a damage of almost 1, a damage of almost 0. Here, and when you do that linear interpolation, as I shown before, you will see that colors that goes slightly above the 1 and slightly down the 0 value here. So if you want to see the real value, use the Gauss plot like this one, okay? The Gauss plot, how does it work? I didn't show it before, but the Gauss plot basically places a particle inside every Gauss point of the element. So you see actually the real position of the Gauss point. And if you want, well, let me remove the grid. Okay. If you want, you can change, the color will be given by the actual value. And the size of the particle, you see that the size is changing, because by default, also the scaling type of the particle scales with the result. So by default, you have the minimum size at 0. If you want, you can also keep them constant. So all the Gauss points will be constant, and you will just see the colors. But actually, this one is quite annoying. You cannot understand what's going on. So that's why the default one is minimum size at 0, and then it increases. If you want, you can scale them. Like I want to make it 3 times larger, so you can see actually what's going on there. Okay. So the Gauss point plot is one other nice feature, and you can see what's going on also here. Let's do a quick animation. Oh, if you want to do an animation, because up to now I just used the slider, but you can actually use the animation also. So you can play the animation, and if you want, you can record the video just by clicking record, choose one of the options, and then play, okay? So this is fine. I think now we can move to, oh, we can extract the load displacement curve. So let me go back to the surface color map. And I select this point, which is the one where we apply displacement. And I want to extract from nodes and from stage 2, which is the pushover analysis. I want to extract displacement versus reaction force in X. This one is micro. Okay, so this is the result that we have for our micro model. As you can see, it's pretty smooth because I used 100 time step. If you want to be more accurate, you can use more time steps, and it will be slightly, you will see more little drops here. But the implex method is quite fine for this kind of analysis. Okay, so this is the result we have with our micro model. Okay, so now the next step, the last step actually now, is to say, okay, well, micro model is fine, it's very accurate, and it is also very fast, because typically it is not fast, but in this case we can use parallelism, as I will show you tomorrow, and we can use the implex algorithm that basically reduce a lot the number of iterations, as you can see, and you are sure that your analysis will converge. So it is a great improvement for micro modeling. But still, imagine that you have to model an entire building and you don't have a powerful enough PC. Probably homogeneous modeling is better. There is another reason why you may want to use homogeneous modeling, is because sometimes you don't have the material properties for the constituents. Now, in this case, this particular example, if you take the paper for the experimental test, you basically have all the data. So you can safely assign the material property to both bricks and mortar, and you're fine. But sometimes, or most of the times, it happens that you don't have all those experimental data. You just have few data on the entire masonry assembly, not only on the constituents. Now, in that case, probably it's better to do homogeneous modeling. But there is a problem for homogeneous modeling. Most of the softwares they either do not have a very good material model for concrete and masonry, or if they have it, it will be very hard to reach convergence with those kind of models. But most of the times they are isotropic. And as you know, masonry is everything but isotropic. It's initially orthotropic, and then it becomes actually anisotropic due to damage. So how you can solve this problem? Well, actually, it cannot be completely solved because it's a very complex model. But there is something that can allow you to have a very good result, and I will show you in a while. So let's keep this one here for comparison. I go back to geometry. I save this one. And now we'll do the same analysis using an homogeneous model, first using an isotropic model, and then I will convert it to an orthotropic one, and we will see how it can match the micro model, okay? So let me save this one, and then I save it with a different name, and we call it macro. Macro. The first time we call it isotropic, and then we convert to orthotropic. So let's see what happens. Isotropic, the first one. Okay. So before doing everything, we start with this one, and we start drawing the equivalent isotropic model. So we just need one face. Now I keep this micro model down here as a background just to draw my model, and then I get rid of it. So at first I draw a 4-node face from here to here, to here. Okay, so we have my first 4-node face here. Then I can copy this one to the top here. And then I can get rid of all the entire geometry. So I have all these two. And then I draw a last face here. Okay, so we have 3 faces. I select them and I click Sew Faces. So now, once again, we are back with just one surface made of 3 faces that are connected. And of course, now we are doing an homogeneous geometry, so we don't need all the drawings for the mortar and bricks. But I started from this model because basically the physical properties will be different, but all the boundary conditions are the same. So let me first assign the element property to everything, because the element property will be the same, a quadrilateral element. Then the boundary condition will be the same. So let's go to condition. And now, of course, these boundary conditions are not applied to anything, so we can just add it. This one was the fix at the bottom, so I can simply select this one, okay. And so I transfer this condition to the bottom of this new model. Vertical load, same thing, add it, and I apply it to the top. Then we have the push, add it, and we apply it to this point. So as you can see, the nice thing of having a user interface, because many people do not understand this, if you had to change that model made in TCOL, it would have been a mess. But when you have a user interface, it's just probably at the beginning you waste a little bit of time, but when you have to do some changes, it's very fast. So the push is there, and now the fixed top, same thing. We have to apply it to here. Okay, let's save it. Okay, the element has been assigned, so if we go to property, everything is transparent, but the element has been assigned. Back to the physical property. Now we need to create an equivalent isotropic model. Now, for the equivalent isotropic model, there are many ways you can compute the isotropic values. The most basic one is that if you have access to experimental tests over the entire masonry assembly, so you need the elastic properties, the tensile strength, intention and compression, and so on. Now, in my case, since I was doing this numerical analysis, I used a concept called computational homogenization. It's something that is not available in OpenSees, but we are going to add it in next month. But it's what I worked on my thesis. and I will just show you, but of course you don't have access now to softwares that does computational homogenization, but you can use any technique you want. You can do a manual homogenization, you can use experimental results. In my case, I used computational homogenization. Now I'm not going to talk about it, but just to give you an image that represents what's going on in computational homogenization. In this technique here, we have a micro model, which is the real model. And then we wanted to simulate the same model with an isotropic one, where the material model is not actually a material model, but it is an RVE, a representative volume element, which has a particular set of boundary conditions. And so when you apply the uniform strain coming from this homogeneous model, this continuum strain will be applied on the boundary in such a way that the average, the volume average of the strain is equal over the RVE. And so the output stress will be integrated over the RVE and will be the homogenized stress, okay? So now, without talking too much about this, this is a technique for which you can use a representative volume element and say, okay, now I push it in the X direction. What is the stress in the X direction? Then I do the same for the Y direction, I do the same for shear, and I obtain all the elastic constants and the strength and fracture energy in the different orientations. Now, this is one technique that will be soon available in OpenSees, but it is not now. Instead, you can use whatever technique you want, either numerical homogenization if you have some access to some solvers, or you can just use experimental results. Now, let's say you have a way to compute these homogeneous models. The first thing that you can do is to, let's say you have access only to an isotropic model. What you can do here. So let me remove the brick. The steel is fine, so I can use the steel. The brick is not necessary. Now I call the mortar. I call it mortar Masonry isotropic. Okay, and then I will change it to orthotropic. This is Masonry isotropic 3D. And then I will change it. Just a second. This is the steel 3D. Let me just change the name just to make everything clear. Elastic 3D, mortar 2D, elastic steel 3D. So we can just assign the steel because the steel will not change, of course. So I need this space in this space, and I drag and drop the steel 2D. In this space, I will assign the mortar 2D that now refers to the Masonry isotropic. So let me change the name. Masonry 2D. So at the moment, this Masonry 2D, as you can see, is referencing the first material model, which is Masonry isotropic. Then later on, we will change it. Okay, so now let's work on this one. Now, basically, in this case, we did some tests, and if you want to compute the isotropic values for this Masonry, we computed on one direction. If I remember correctly, it was an homogenization done along the X direction of the Masonry. But you can do the same along the Y direction. In either case, in one case, you will overestimate the response because the strength on the other direction will be less, or you will underestimate the response if you do the homogenization on the weak direction. Then you will see that when we will use the orthotropic mapper, everything will be fine. So I think now here we made an homogenization along the strong direction. So the Young modulus was 8940, 0.17 for the Poisson ratio. The tensile strength was 0.94. Yes, it was pushing in the X direction. That's why the tensile strength is more than the tensile strength of the bed joint. The fracture energy was 0.21. Then we have 6, 10.4, 1.5, 0.0018. Then we have 30 as fracture energy in compression, and 0.9, 0.2, and 2. Now these three values are not chosen randomly, but we have chosen it trying to best fit the experimental curve given by the RVE. And then we have a Rankine surface here. 1.16 was fine for the biaxial strength obtained. the latency was very high, so we put just 0. This is fine, and 0 everywhere. Simplex algorithm, automatic regularization. Okay, so these one are the isotropic homogeneous values obtained from an homogenization along the x direction. And in fact, you can see them from the higher tensile strength. In fact, when the equivalent tensile strength along the x direction is slightly higher because you just have 2 layers of head joints parallel to the orthogonal to the load direction, but then you have 2 layers of bed joints that act in shear, and this will actually increase the overall tensile strength in that direction. Well, of course, if you do the homogenization in the y direction, you will obtain exactly the tensile strength of the mortar joint because it is in series. Okay, so this is fine. Now, if we use this one, we can just create the mesh and run the analysis. So global seed, this mesh is fine. Or it was like, we can use a smaller mesh. It was like 75, I don't remember. 100, no, it was too much. 50, yes, it was 50. Then the mesh control over faces, structure, quad. Select everything, assign, done, and we build the mesh. Okay, let's save everything. Let me change the name of the recorder, because now this one is macro plane isotropic. Let's call it isotropic strong because it is along the strong direction. Save it and run the analysis. Okay. Well, just to show you the convergence rate, as you can see here. Just 3 iteration every time. Then you go from the first error to the -14. This is due to the Implex algorithm. Okay, so we go back to the post-processor. This one was the first database of the micro in plane. Then we can load another database. I didn't show you before, but in STKO, you can load more database into a single post-processing session. So you can compare results, okay? So here we load a second database, which is macro in plane iso strong. Is the second one. Now we can create a new plot group. Let's call this plot group micro. Okay. Now we create another plot group, which is macro iso. Let's create a surface color map. And this is what happens, okay. Let's see it a little bit more deformed. Okay, if you can do a single animation, pretty much the failure mechanism, of course, is the same. But it is very clear the failure mechanism of this kind of wall. But if we extract the load displacement curve, we will see some difference. Since we homogenized along the x direction, we will see an overestimated result. So I want to extract on node. Now I want to extract not from the first database, but from the second one. Second stage, displacement versus reaction force. And I want to call this FU macro isotropic. And I don't want to create a chart because I'm going to overimpose it on the previous chart. So I don't want to create a new chart, just the chart data, which is this one. Then I go here and I load it. So this is what happens. You see a quite large overestimation, okay? Doing the homogenization along the y direction. Now imagine if we had done the same homogenization along the weak direction, probably what would happen is to have an underestimation of the strength. Okay, now let's see this orthotropic mapper, what it is able to do. So back to the preprocessor, save this model. Now I save it with a different name, macro ortho. Okay. Now to convert this one into an orthotropic material is pretty simple, but as I told you, you need experimental results or computational results over the 2 direction So as we did the homogenization in one direction, we need the property also in the other direction. And then we can use a material model which is called orthotropic mapper, and is based on the mapping of tensors. If you want a reference for this, there is a paper by Professor Luca Pelà and Miguel Cervera, which is this one, and I will send you the reference, which basically explains you how this simple method works. It is a simple linear process. It doesn't include any external linearity. It just takes the strain from the orthotropic space. It maps the strain into an isotropic space using a particular mapper. Then you do the calculation on the isotropic space, and then the stress obtained from the isotropic material will be transformed to the orthotropic space back, okay? And then this matrix, which is called the tensor mapping, depends on the ratio between the elastic constants for the orthotropic material and the isotropic material, and the ratio between the strength of the isotropic material and the orthotropic material. So I will give you a brief introduction here, then you can read more information on the paper. So let's create a Masonry orthotropic. Masonry 3D ortho. Then we go under model, material ND, other ND material, and here we have an orthotropic material. No, sorry, it's under Asgard software. Orthotropic material. Okay, so what do you have here? It is a mapper, so like the plane stress or the plane strain, but of course here you have some parameters. So the first one is the 3D isotropic material that you want to convert, and it is the Masonry isotropic 3D. Then here you need the elastic modulus, or every elastic constant, so elastic modulus, shear modulus, and Poisson ratios for the orthotropic elasticity of the Masonry. So you need to compute from your tests all the elastic constants to construct the orthotropic material, okay? And of course, for an orthotropic material, you don't need just the Young modulus and the Poisson ratio, but you need all these components. And this specific example, it was along the x direction, the 8940, the same one that we had before. So it is equal to the isotropic one because the isotropic one was mapped into the x direction. And in the y direction, it was 4320. Same in the z direction. It is not exact in the z direction, but we are not analyzing it in the autoplane. So then the shear modulus, we make it the same. And then the Poisson ratios. 0.17 and 0.17 here. Then here you have something different. So this one is the elasticity. These ones instead are all the parameters required to create the tensor mapping. So this one is the part that will map the strength in the different direction from the isotropic to the orthotropic. So for example, the factor A sigma XX, this one is the ratio between the isotropic strength in x direction and the orthotropic strength in x direction. And x direction, as we said, is 1 because I already have in the isotropic material the same strength that the orthotropic material has in the y direction, in the x direction, sorry. While in the y direction, the isotropic material is overestimating what was happening in the real orthotropic y direction. And with some tests, we found that in the y direction, the strength is actually half the one in the x. Then in the autoplane, we don't care, so we just put 1. And the shear in the isotropic material is 2.61 times higher than the orthotropic one. So we put this scale factor here. And for the autoplane shear, we just put 1 and 1. We don't care about them. Okay. Here you can do some quick tests. For example, let's say that I want to, let me save it first. Let's say that I want to test it in X, in tensile response, so monotonic, monotonic. In the tensile response, let's say 0.01 in tension. Okay, let me, okay, the tensile fracture energy is quite high here because it is not regularized. So let's push it a little bit more. But what I want to show you is that in X, you have the same thing we have seen before, 0.9. And now if I do the same along the Y direction, should be 0.45 more or less, because it is 2 here. So let's go here. Let's see what happens in the second direction. Oops, I set 0.22 is fine. Okay, 0.45, which is exactly the value that we decided before. Okay, and the same happens in compression and shear. Now, you have this material, you can play with it, you can try to understand how it works, you can read the paper for more information on the computational part. So it is pretty simple to use. The only problem is that you need some information about the experimental results, or in a few months, we will have the computational homogenization also in OpenSees, and so it will be everything automatic. Okay, so this is fine. Now we just need to move it just after the Masonry isotropic, because now I want to take the Masonry 2D that before was converting the isotropic one. Now let's make it convert the orthotropic one. So in this way, we are converting the orthotropic 3D into an orthotropic plane stress, which is the same that is assigned here. Okay. So we are almost done. We just need to change the name of this thing into ortho, so we can do a last comparison. Orthotropic, save it. I just changed the name of the recorder in such a way that I do not overwrite the previous results. And let's do a run. Okay, same convergence rate we had before because we didn't introduce any nonlinearity in the process. This mapping is linear. Okay, so let's load another one. Third is the Masonry ISO orthotropic. A new one. Let's call this one macro ISO. And I want to add a surface color map also here. So the what happens is basically the same. So same failure mechanisms. Okay, nothing about it. Now let's see what's going on in terms of force versus displacement on nodes. But the source database should be macro IP ortho, macro, sorry, stage number 2, displacement versus reaction force. Next, and let's call this one macro ortho. And also here, I don't want to create a new chart because I'm going to overimpose it here. Finish. We have the data here. We go back here and we add the orthotropic. Now, as you can see, look here at the orthotropic, how good it maps the microscopic one. Now, just to show you the little difference, because they have a meaning, this kind of difference are expected. You cannot expect exactly the same results, of course. Let me remove the isotropic one because it is increasing the scale. Okay, look here. The results are quite very good, actually. There is a reason why the orthotropic homogeneous one is kind of overestimating the energy dissipated in the first place here, and then it falls more rapidly than the orthotropic one, the microscopic one. There is a reason, but the nice thing is that the elasticity is taken very good, and the peak strength in terms of both strength and capacity is the same. Okay. Now these few differences, they have a meaning. So the first one, it looks like in the first range. Oh, let me go back to the micro, because it's easy to understand what's going on in this one. So in the first range, this kind of walls, they always show, let me go to damage because it's easier to explain this showing the damage. Fix from 0 to 1. Okay. So in the first stage of the analysis, the first nonlinearity that you have is this kind of opening of horizontal cracks. This one basically translates into this loss of stiffness. Okay. Now this one happens faster in the micro model rather than in the homogeneous model, because actually here the crack is much smaller, so this one will localize very easily. While instead, if you go into the microscopic one, when this one tries to localize, the element is larger, and it is a mix of mortar and brick. So it's like mortar and brick, but spread over the entire element. That's why this one will kind of take more time to open the crack in that direction. Okay, so it makes sense that it takes a little bit more time here. The next thing is that the peak strength is basically the same, is where the crack coalesce into a single crack when we go in the micro model here. But then the softening regime, of course, it will be faster in the macro model rather than in the micro model, because in the micro model, the crack is not a straight crack. Let me show you this topic by scaling a little bit.
Excuse me, Professor.
Yeah.
So minimizing this difference between the micro and macro, as you showed us, if we change the motor property, we can minimize the difference, right? For example, if we decrease the strength of the motor in the motor material properties, we can minimize the difference between the curve of the macro and micro, because as you mentioned, the initial stiffness is because of the cracks produced in the motor joints. So
yeah, actually, but if you increase the difference, if you increase the difference between mortar and brick, you will increase the difference here. Because if you decrease well, actually, first of all, you don't have to change the material properties of the mortar because they come from an experimental test.
Yes, exactly.
So it is not that. But let's assume that you have an experimental test where the mortar is, let's say, 10 times even weaker than this one. It will happen that in the micro, it will break even faster. While in the macro model, it will still be a mix of, it is an homogeneous model. So at the end of the day, it is a mix of mortar and brick. That's why it will take, and that is not the only problem actually, it's also the mesh size. There you have to break an element which is kind of larger, so it will take much time to dissipate all that energy. Here you have to dissipate a smaller amount of energy. So in any case, this first kind of cracks here will break more easily in the macro model, okay? Because they are aligned, the elements are smaller, and they are all made of the weakest material, okay? But now, in the post-softening regime, it happens the opposite. So the isotropic model breaks easier than the other. But this is because of the same reason, but on the opposite side. When the micromodel is trying to break into this line, which overall is a diagonal line, it is actually not like that. So you see a combination of tensile crack in the bricks, sliding in the mortar joint, and only tensile failure in the head joints here. And of course, the path is not linear, so it takes some time for the crack to reach the two different toes. Okay. Well, when you see the same thing in the microscopic model, it is completely different. So here, since the mesh is uniform, and once again, the properties are homogeneous, in this case, this homogeneous property will be slightly softer than the orthotropic one, because you don't have the strong intrusions made by the bricks, okay? So all those interlocking problems are not there. So it's easier to form a crack in this kind of mesh pattern. That is the only reason. But this is necessary. I mean, you cannot expect these two results to match completely. There should be a difference, otherwise it will be fake.
So you mean it's only
just a linear path,
you mean it's only depend on the motor strength? I mean, the difference is
on the
difference is because of the motor strength. If it is great, the strength is, if the strength is greater, the difference may be minimum. If the strength is lower, the difference may be maximum.
Yeah, it's a relative difference. I mean, it's obvious that the less is the difference between mortar and brick, the more the material will be isotropic. That is obvious. The strong orthotropicity of masonry comes from the strong difference, both in stiffness and strength, of mortar and brick. So it makes sense that the more these two materials are equal, the more the mapping will be the same, but because then the material tends from being orthotropic to isotropic.
Yes.
But what I want to say is that this kind of mapping is quite very useful because it is a simple linear mapping, and as you can see, you capture the overall behavior. So at least the stiffness, then the strength and capacity, and of course you have some difference, but it is what is expected. I mean, you cannot expect to have a completely overlapping, but also in terms of computational cost, it is much smaller. Okay, so I think we are done for today. So we have other 10 minutes for questions, and then we will do the same thing that we have done now, Wednesday, for the out of plane. And there I will show you some extra concepts that you have to take care about. So if there are any questions.
Maybe I can add something also. I think the presentation was very interesting and Guido Kamata. And what I want to point out is the fact that the analysis run in few seconds. You can run a micro model in few seconds. You can run a macro model in few seconds. And the results are really, really good. The macro model is very similar to the micro. And Massimo Wednesday is going to show that with the parallel version, you can run entire buildings without problems. Also, thanks to the efficiency of the algorithm that is using in Inflex. So, few iteration, you get to the solution. So, I think it's something really, really particular what it's showing, and was very also, I think, interesting how we showed the calibration of the model. And if you have questions, also, it'd be very interesting to answer. There's a question, Massimo. Look at the chat.
I don't. Oh, I didn't receive any. For some reason, I didn't receive any. Oh, here it is. I'd like to ask for how long the software's license is valid. Oh, okay, it will be valid now. The first installation will be valid for 1 month, but then we have your registration, so you just send us an email and we will extend it for other 2 months. Okay. So when it is going to expire, send an email saying you were on the on this webinar, and we will extend it. So hope you will enjoy the use of STKO in these 3 months. So we'll try to get the best out of it. I missed how 2 elements can be attached and how to visualize the load and boundary condition. Okay, so let me just go back. Let me share my screen. When you have 2 different geometries, now I'm going to draw them once again here. Let's say you draw one first geometry here, then you draw another one here. Now these 2 geometry have an edge which is overlapping, but they are not the same edge. As you can see here, there are 2 separate geometry, one here and one here. If I mesh them, they will be actually separated. So if I want to make them continuous, I just go into the sew face command because they are faces, or in the general case, I can use the merge command. Now in this example, I use sew faces. Then I select this one and this one, right click, and they will become a single geometry, which is this geometry here. I can obtain actually the same with the merge command, but the merge command is more powerful. It's made for general purpose Boolean operation. For example, let's say I have 2 faces, then I have a line passing through here. And then I want to merge everything. So I click on merge, I select everything, right click, and then what you obtain is a complete geometry made of the intersection between these two, okay? And then how to visualize the boundary condition, you just need to go on the condition tab. So when you are on the condition tab, you see conditions. When you are on the mesh tab, you see the mesh. Of course, now the mesh is gone because I changed the geometry. When you go on the property tab, you see the properties, okay? So we have a few more questions. Okay, here we answered. After the 3 months, how much will it cost if we want to use the software further? You can see the price table on the website, but it is actually very cheap for research purposes. Then we have also discounts for research purposes and or classrooms and so on. But if you go on the ASDA software, there is the STKO tab with the price table there. Okay. Is there any limitation of commercial or student version? No, actually, we have the research version that does not any limitation. The only limitation is that it can be used only for research. I mean, it is not a commercial license. For a commercial license, you have to contact us because the commercial license is a different topic. But research, it means you can be used by student, classrooms, professors, researchers, and it has no limitation. Okay, it's just cheaper than the commercial version, of course. Is it possible to model individual rebars together with shell elements? Of course, actually tomorrow, at the end of the day, we will show some large models that we run with the OpenSees MP. No, actually not tomorrow, sorry. I keep on saying tomorrow, it's Wednesday. I will show you a simulation of experimental test on a reinforced concrete column, where the entire column is made with solids and all the rebars and stirrups are modeled with fiber beam elements, okay? And of course, it can be done also with shells, but I will show you with solids directly. So I will show you how to connect beams with solids, how to create stirrups, and how to do a very detailed analysis of a concrete member. Will this webinar be uploaded at the ASDA YouTube channel so I can review it in the next time? Yes, it will be on the ASDA YouTube channel, it will be on our website, so you will be informed, okay? But in any case, it will be available, yes. Okay, so let me see. I would have a question on regularization. Is it applied also by OpenSees to ND material models? No, that's the problem. OpenSees has a function in the element and this function is able to give you the characteristic length. But then it's up to the guy that implements the ND material model to take this characteristic length and use it for regularization. And as far as I know, this material model is the only one that is using it. Few others, because this material model has been requested, this get characteristic length function has been requested to Frank McKenna by another guy that was placing a concrete model in there, but this concrete model is not there anymore. So as far as I know, the strain regularization is only done by our material model. Okay, so it's up to who implements the material model. It's not something automatic. It cannot be automatic because it depends on how the material model works. Or we just can model those dampers as spring link element. Is it possible to model shared panel damper in STKO as solid model like in Abacus? Well, I think you can model them, but probably using simplified models, like you said, springs and links, it will be easier, for sure. In any case, you have both options.